In this example, I'd like to analyze a simple crane system. So I have a crane arm that goes from A to B, and then there's a cable that goes from B to C, and that goes out to the tip of the crane. The crane is supporting a load of 5 kips at B, and midway along the crane arm there's also a load of 2 kips. Okay, and the crane arm is at an angle of 30 degrees and the cable is at an angle of 20 degrees, both with respect to the horizontal. And I'd like to determine the tension in the cable for this configuration and the support forces in A, assuming that the system is in equilibrium. So to start, make a free body diagram. And if I make a free body diagram of the crane arm, I have the 2 unknown support reactions in A, AX, and AY. And I have the tension in the cable. And the cable is a 2-force member, so I know the line of action of the tension is along the cable. So that gives me the direction along which the tension acts in the point B. So that's minus cosine 20 EX minus sine 20 EY. So and 20 is the angle of the cable with respect to the horizontal. So I can now use my equilibrium equations. So I have the sum of the forces in the horizontal direction, or the x direction, gives me AX minus T cosine 20 equals 0. Sum of the forces in the vertical direction, so the y direction, is going to be AY minus 2 minus 5 minus T sine 20 equals 0. And I have to pick one point to sum the moments about, and I'll go ahead and pick point B. So I sum the moments about point B in the orientation shown, and I have the lever arm times the forces. So 20 times 2 times cosine 30 gives me the moment associated with the force in the middle of the crane arm. And then I have minus AY 40 cosine 30 is the moment associated with AY, plus AX 40 sine 30 gives me the moment associated with AX, and that all has to equal 0. So if I want, I can arrange these in a matrix here. So I have a system, it becomes more apparent that I have a system of 3 equations and 3 unknowns. My unknowns are AX, AY, and T. And I can go ahead and solve this system of 3 linear equations, and I find then that AX is equal to 28.1 kips, AY is equal to 17.2 kips, and the tension in the cable is 29.9 kips, or basically 30 kips in the cable. So this is just a simple example of the application of statics in a 2-dimensional setting to a simple engineering problem. So one thing to notice about this problem is that there were 3 unknowns in the problem. So there were the 2 support reactions at A and the tension in the cable, and there were 3 equations of equilibrium. So I had the same number of equations of equilibrium as I had unknowns in the problem. And when you have that situation, we call the problem statically determinate. So we're able to determine the unknowns of the problem using statics alone. Okay, now this isn't always the case. Consider this beam here supported at A and B by fixed pin supports. If I draw the free body diagram for this, I end up with 2 unknown support reactions at A and 2 unknown support reactions at B. So there are 4 unknown support reactions in total in this problem. So in this situation here, we say that the problem is statically indeterminate. It's indeterminate because I only have 3 equations to determine 4 unknowns, so there are not enough equations to determine the unknowns of the problem. So we call it indeterminate or statically indeterminate. In general, there's a bit of more terminology that goes with this. If we take the total number of unknowns and we subtract off the total number of equations of statics we have, the difference is something that we call the degree of indeterminacy of the problem. So if the degree of indeterminacy is equal to 0, it's statically determinate, and if it's greater than 0, then we're going to have a statically indeterminate problem.